Hi, welcome to Algebra 1, Lesson 9-3, Rewriting Radical Expressions. Then you'll be able to write equivalent radical expressions. The lesson vocabulary is product, property of square roots. So as the name tells you, we will see a property that has to do with the product or the multiplication of square roots. So let's start with explore and reason. The table shows the relationship between the area of the square, the side length of the square, and the square root of the area. A square with an area of 4 and a side length of 2 is shown at the right. So we have a side length of 2 and the area of the square would be 2 times 2, which is 4. So 4 is the area. And then if we square root the area, then we get a side. So this is the relationship of the square root with the sides, right? So the area of the square, if it's 1, square root 1 would be 1 because 1 square would be 1. So we're thinking opposite ways when we're thinking about roots. So when the area of the square is 4, then we have a side length of 2, 9, 3, and all that. These are called perfect squares. And perfect squares will have integers as their root. So yeah, any number between 1 and 4, like root 3. 3 would not be a perfect square, so root 3 is an irrational number. But any perfect squares like these are going to be rational number because they're integers. So part A, what is the side length of a square with an area of 49 square units? So if we have a 49 square units, what would be the side? The square root of 49. What square would be 49? 7, right? So 7 squared is 49. So 7 units. Between what two consecutive integers is root 20? How do you know? So root 20 is an irrational number. It's going to be a decimal that's non-repeating, non-terminating. So between what two consecutive integers? Consecutive means right after each other in an order from least to greatest, right? So two consecutive integers. So basically, which two perfect squares is root 20 between, right? So root 20 is over here, which is between 4 and 5, right? So yeah, 4 and 5. How do we know? Because root 20 is between root 16 and root 25, which is 4 and 5. Okay, so think of 3 squares that have a side length between 3 and 4. What is the area of each square? So anything that has a side length between 3 and 4, 3.1, 3.1. If the side length is 3.1, then the area is 3.1 square, which is 9 point what? 9.61. And then if the side length is 10.24, then the area would be 10.24 square, which is going to be 104.8576, right? Yeah. So so these are not going to give you a perfect integer as a good integer as your areas. Okay, let's look at an essential question. How does rewriting radicals in different forms help you communicate your answers? So radicals are any numbers that has to do with the roots. So we're going to learn how to rewrite radicals in different forms and see how that helps us communicate our answers. So let's start with example 1. Use properties to rewrite radical expressions. How can you visually visually show root 16 is equivalent to 2 root 4? So 16 root. So 16 is going to be the area of the square, and the root of 16, square root of 16 would be each side, would represent each side, right? So how can you visually show this is equivalent to 2 times root 4? So 1 root 4 is this small square where area is 4, but the side would be root 4, right? But the side of the side of the square that has an area of 4 would be 2. 2 plus 2 is the same as 4, right? So visually, you can use the square boxes to visually prove that they're equal to each other. So the sum of the lengths of two smaller red lines here would be equal to this big red line. So how can you compare root 20 and 2 root 5? So using similar ways, if we have a square that has an area of 20, which is not a perfect square, but we know it's going to be between two perfect squares, right? And then we have 2 root 5. So we have this property now. The product property of square roots states that root a times b is equal to root a times root b. So you can, when a and b are greater than or equal to 0, because when they are negative, it's impossible, right? It's not going to be a real number. So it has to be both positive, but you can separately divide these a and b, these factors, into different square roots, okay, and then multiply them, and it'd be the same thing. So use properties of square roots to show an equivalent expression for root 20, which basically you want to look at the factors of 20, right? So if you use division, you'll see that 20 with prime factorization would be 2 squared times 5. And then, and then you can rewrite that as root 4 times root 5, because root 4 is basically 2. So then you can simplify this and say root 20 is the same as 2 root 5. So the radical expression root 20 is equivalent to 2 root 5. Okay, so remember this product property of square roots, and we're going to use that in try 1. So in the next page, compare each pair of radical expressions in parts A and B. You can use different forms to compare them. So you can simplify the roots as much as possible and compare them, or use perfect squares to compare them. So pause the video, see if you can do it by yourself. Come back when you're ready for answers. Okay, are you ready? Let's look at part A. Square root 36. You know that this is equal to 6, right? 6 square. You can factor it out and say, 6 square. Root and the square are inverse operations, so it's basically 6. So that's 6. And 3 root 6 is actually 3 times root 2 root 3, right? So then, another way to rewrite this would be 3 is really 3 square root, right? Root 3 square, because that's really root and 2. Again, they cancel each other out, so that's like doing nothing. And so root 3 square times root 6 is the same, is equivalent as 3 root 6. And so that's equal to root with the product property of radicals, right? 9, it's the same as 3 squared times 6, which is 9 times 6, which is 54. And so if we change the forms, we can easily compare. Root 36 is less than root 54, obviously, because 36 is smaller than 54. So, and so root 36 is less than root 54. Okay, let's look at part B. 6 root 2 and root 72. So using the same way, we're going to use the product property in the opposite way. So 6 is the same as root 6 square. So times 2 would be the same thing. So then that is equal to 36 times 2, which is equal to 72. Right? So they're actually the same thing. So 6 root 2 is equal to root 72. And you can compare those two. Okay, good. So let's look at example 2. Write equivalent radical expressions. What is an equivalent expression for root 63? So root 63, you can also factor this out into 9 times 7. And 9 is actually 3 squared. So then you can separate that and simplify into 3 root 7. Right? So the expression root 63 is equivalent to 3 root 7. So let's look at try number 2. Rewrite each expression to remove perfect square factors other than 1 in the radicand. So rewrite the expression so that you can take out all the factors as possible from the root. Pause the video, see if you can do it by yourself. Come back when you're ready for answers. Okay, are you ready? So factor out 44. 44 is really 2 times 11, right? So, wait, 2 times 11, sorry. So then this is root 2 squared times 11, which is root 2 squared, or root 4 times root 11. So it's root 4 times root 11, which is 2 root 11. I'm just trying to write as many steps as possible in case you are wondering. Part B, 3 root 27. 27, if you factor it out with prime numbers, you have 3 times 9, 3 times 3, so 3 cubed. So then you have 3 root times root 3 to the third power. So then you can only take out 2 3's because, you can only separate it using root 9 and root 3, right? So root 3 is still root 3. So then finally you have 3 times 3 root 3, which is 9 root 3. Okay, so that's all we can do for now. All right. That wasn't too hard. Let's look at example 3 now. Write equivalent radical expressions with variables. What is an equivalent expression for root 63 x to the 9th power? So now we may have to factor out even further. So if we have a variable inside, we can also factor out the variable. So use as many factors as possible. Okay, so 63 is 9 times 7, or 3 times 3 times 7, right? And x to the power of 9 is x times x times x 9 times, right? So you can rewrite that using even number powers, or you can rewrite it using squares too, right? So x squared times x squared times x squared times x squared times x would be 2 plus 2 plus 8 plus 1, right? So then, you can list all the factors as you would like to, and that's all in the square root. That means that 3 would come out, and then 7 would still be there, but there would be 1x, 2x, 3x, 4x, x to the power of 4. And then you have 7x still in the radicand. So this is an easy way to visually cancel it out and see if you have any factors left over. So factor out as much as possible, separate them using the roots if that's something that you prefer. But you could also factor everything out in the square root and pull them out from the radicand. Okay, so the expression is equivalent to 3x to the 4th power root 7x. Let's look at try number 3. Rewrite each expression to remove perfect square factors other than 1 in the radicand. So Yeah, so take out as many factors as you can from the radicand. Pause the video, see if you can do it by yourself. Come back when you're ready for answers. Okay, are you ready? So 25 is a perfect square, right? So then you already know that it's going to be 5 squared times x squared times x, right? So then you can have 5 times x times root x. So then it's just 5x root x. Okay, part B. 5 is already outside, so 5 is here. And then root 4 is 2, right? And then root x to the 17th power. You can rewrite this with even number of powers. So let's say, x to the power of 4, x to the power of 4. So that's 8, x to the power of 4, 12, x to the power of 4, 16, and then we have x. So then x to the power of 4 root would be x to the power of 2, x squared. So we have 5 times 2 times x squared, 1x squared, 2x squared, 3x squared, and then 4x squared, and then root x, right? Why am I writing the powers as I'm counting? So 2, 3, 1, 2, 3, 4, 1, 2, 3, 4. Okay, and then root x. So then we have 10, and then x to the power of 2, 4, 6, 8. Remember the properties of exponents. Don't multiply the powers. You need to add the powers when the bases are the same, right? And then you have root x. There we go. That was example 3. We can look at example 4 now. Multiply radical expressions. How can you write an expression for the product of 3 root 5x times 2 root 15x cubed without any perfect square factors in the radicand? So now we have like 2 different terms, but it's the same rule. You just have to do it step by step. So factor everything out. 3 root 5x is already factored out as much as possible, right, and simplified. 2 root 15x cubed needs more factoring inside the radicand, right? So then you have 15 that could be factorable by 3 times 5, and then you have x cubed that could be rewritten as x squared and x, but then you could also combine all the radicands in one so that you can group them and take them out, right? So then you have 3 times 2 outside the radicand, and then you have 5x times 15x cubed. So 5 times 3 times 5 times x to the 4th power. So then we have 3 times 2, which is 6, and then we have 5. So 6 times 5 is 30, and then we have 3 in the radicand still, but x, the variable would all come out and be x squared. So then it would be simplified to 30x squared root 3. So the expression is equivalent to 30x squared root 3. Okay. So let's try number 4. Write an expression for each product without perfect square factors in the radicand. Pause the video, see if you can do it by yourself. Come back when you're ready for answers. Okay, are you ready? Let's look for A. We have 1 over 2 times 4, so 1 over 2 times 4 together. Now everything together in the radicand, 21x cubed times 7x squared. And so 4 divided by 2 is 2. And then 21 is 3 times 7. So we have 7 squared inside the radicand. Then we have x to the power of 5. We can rewrite that as x to the power of 4 times x, right? So then we can simplify this into 2 times 7, and then times x to the square, and then root 3x. And so that would be 14x squared root 3x. Okay, let's look at part B. 2 root 12x to the 9th power times root 18x to the 5th power. So 2 times 1 is just 2. And then you can combine everything in the radicand. 12x to the 9th power times 18x to the 5th power. And so that would be 2 times, we can factor this out. 12 is 2 square times 3. And then 18 would be 2 times 3 square. And then x all together combined would be x to the power of 9 plus 5, 14. And so we have 2, and then this can come out, right? Times 2, times 3, and then that's just 6. And then wait, x to the power of, that's really to the power of 4. How many 2's are there? So 14 divided by 2 is 7. So we have x to the power of 7, right? And then root 3 times 2 would be 6. Okay, and then simplify everything. That would be 2 times 2, 4 times 3, 12. X to the 7th power, root 6. There we go. Okay. Good. So now let's look at an application problem. Example 5. Write a radical expression. A light fixture in an ice cream shop is in the shape of an ice cream cone, and the cone has a height that is 7 times the radius. The expression for the slant height is root r squared plus h squared, where r is the radius and h is the height of the cone. The slant height should be no longer than 24 inches to fit on the wall. What is the slant height of the cone with the radius shown? So we have a height over here, the vertical height itself, that's vertical to the ground. Slant height is this height, that's slanted. And then we have a radius, that's 3 inches. So we have a triangle here, right? So triangle means and this is a right angle because that's the height, that's vertical to the ground, and then radius would be horizontal to the ground. So then we know that we can use a Pythagorean theorem where the slant height would equal to r squared plus h squared. A square of slant height would be equal to r squared plus h squared. That means a slant height would equal to root r squared plus h squared, which is given. Okay, and so and we know it should no longer be 24 inches to fit on the wall. So this is actually an inequality solution where it should be no longer than. But it could be equal to 24, right? But it can't be longer than that, 24 inches. So, yeah. So here, it's already shown that the radius is 3. So we want to check if this is true, if it's true that it's smaller than 24 inches. So let's plug it in. 3 square. And then height, height, we know that there's another information here. Height that is 7 times the radius. So height, h is equal to 7 times 3, which is 21, right? So then we have r squared plus 21 squared, all of that root. And so that is equal to 9 plus 21 squared would be 441, and that's equal to root 450. And then root 450, if we factor this out, let's see, let's factor out using prime factors. Divide by 5, we get 45. Divide by 5 again, we get 9. Divide by 3s. Okay, so root 450 would be 2 times 3 squared times 5 squared. And so that's equal to 3 times 5, 15 root 2. There we go. So 15 root 2 is about if you can use your calculator at this point, is about 21.2132 inches. So is that less than or equal to 24? Yes. So it will fit on the wall. Would be our last solution. Okay, good. So let's look at triad number 5. Another cone has a slant height s that is 5 times the radius. What is the simplified expression for the height in terms of the radius? So see if you can understand what the problem is saying. Pause the video, solve it, come back when you're ready for answers. Okay, are you ready? So using the same situation in the equation, right? The slant height is equal to root r squared plus h squared. Instead of the height now, right? Wait, instead of the radius that's given, we know that the height is 7 times radius. So then, and s is 5 times the radius, so we can rewrite this equation in terms of r, right? 5 times r would be the slant height. Then root r squared plus 7 times the radius would be, would be our height. And so we want to simplify the expression, solve for the height in terms of the radius. Oh, okay, so we're not doing 7 times r. We're just solving for h. So so we want to solve for h. That means we have to square both sides. And then we have 5r squared is equal to r squared plus h squared. That's equal to 25r squared. And then we can subtract r squared on both sides. And then that's equal to, these are like terms, right? The powers are the same. So it's 24r squared is equal to h squared, and now we root both sides, and we have root 24r squared is equal to h. So if we simplify this, we have r, because r squared is canceled out by the root, and then root 24. So let's factor 24 out. We have 2 divided by 24 divided by 2, 12 divided by 2, 6 divided by 2, and so we have 2 squared times 2 times 3. And so h is equal to 2r root 6. Okay, so that's it. That is the simplified expression for the height in terms of the radius. So when we want to find an expression in terms of something, that's what it's doing for like an x in a general linear equation, right? We're solving for y usually and using x to write an expression. So that's what we're doing. We're writing in terms of the input, and then we're going to solve for the output. Okay, let's summarize our lesson. Rewriting radical expressions. A radical expression is written in simplest form when there are no perfect square factors other than 1 in the radicand. So we have a product property of square roots that says we can separate the factors, but keep the radicands inside as long as they're positive. And so these are the numerical examples for different ways to rewrite the radical expressions. All right, so that was lesson 9-3, rewriting radical expressions. We'll continue with the next lesson in the next video. Bye!